Electric and magnetic fields are visualized using field lines or field vectors. In general, field lines may be categorized into three situations that are illustrated here. Field lines may have a start and a finish. They may reconnect by falling back on themselves, or they may start in infinity and finish in infinity. Field lines never cross because at the crossing point the field would not be uniquely defined. The cases shown here are the only three possibilities, and they are mutually exclusive. The start point of a field line is often referred to as a source, and the finish point is referred to as a sink. The idea here is that field flux flows from the source to a sink. As vector fields, the electromagnetic fields are defined for the entire space. The 3 points indicated in red, blue and green are of particular interest. These 3 points can be distinguished. The source of field lines has a positive divergence. The sink of field lines has a negative divergence. And centers of circulation have a non-zero curl at that point. Divergence and curl refer to mathematical operations that determine the change of the vector field at that point in a certain way using partial differentiations. The divergence operation determines the net change of the field at that point. Quite differently, the curl operator assesses the rotational behavior of the vector field at that point. The 3 types of points are characterized by the fact that the respective differential operation returns a non-zero result. A positive divergence identifies a source, a negative divergence identifies a sink, and a non-zero curl identifies a center of circulation. From the sign of the curl, it can be decided if the circulation occurs in a right-handed sense for a positive curl or in a left-handed sense for a negative curl. The mathematical definition of the divergence operator is shown here. In Cartesian coordinates, the divergence of a vector field V is equal to the sum of the partial differentiations with respect to x, y, and z. In other coordinate systems, such as in cylindrical or spherical coordinates, the divergence operator takes a different form. This is shown here for cylindrical coordinates. This form can be obtained from the Cartesian form using coordinate transformations. Notice in particular that in front of some of the partial differentiations there is now a factor that is different from unity. In this case, the factor is equal to 1 over the radial coordinate. It is immediately obvious that a constant vector field, constant in magnitude, constant in direction, does have a divergence of 0, because all 3 partial differentiation give 0. Since the divergence of a vector, calculated at a particular point in space x, y, z, or r, phi, z in cylindrical coordinates, is the net change of that vector at that point, the divergence is always a scalar. The mathematical definition of the circulation probe of a vector field, the curl operator, is shown here. In contrast to divergence, the curl of a vector field V is also a vector. As with the divergence vector, a coordinate transformation transforms the curl operator into a different form, as shown, for example, here for spherical coordinates. An equivalent expression exists for cylindrical coordinates. Notice that in the form for spherical coordinates, there are factors different from unity in front of some of the partial differentiations, and also inside their argument. For example, in the case of the r coordinate of the curl operator, there is a factor of 1 on r sine theta in front of both partial differentiations, and in the argument of the theta differentiation, there is a sine theta. Independent of the form and the coordinate system, the curl of a vector, calculated at a point in space x, y, z, represents the circulation of the vector field with respect to that point. The curl of a vector is itself a vector. Shown here are 3 examples of vector fields, and the divergence of these vector fields is probed at 3 points indicated in red and blue. For simplicity, the 3 examples are kept to 2 dimensions x and y. In the first case, the vector field is a constant vector field. At the red point, the field does not change in x direction, therefore dx vx equals 0. It also does not change in y direction, therefore dy vy equals 0. Therefore the divergence of the vector field v at the point red is equal to 0. In the next example, the vector field is constant in direction but increases in magnitude with x. Since this increase is assumed to be linear, the differentiation with respect to x or vx is constant. The divergence of the vector field at the red point is therefore equal to that constant. In the final example, the vector field is constant in its lower part. However, there is a change in magnitude and direction as the y-coordinate increases. The red point is at the position where this change occurs. Therefore, dx vx is equal to 0. However, dy vy at the red point is larger than 0, because the direction changes. Thus, the divergence of the vector field at the red point is different from 0, being equal to a constant c2. At the blue point that has a larger y-coordinate, the divergence of the vector field is however again 0, since here magnitude and direction of the vector field are constant. Historically, the concepts of divergence and curl have their origin in studies of fluid dynamics. This provides for nice analogies to their use in electromagnetism. Again, sticking to 2 dimensions for simplicity, consider a large lake with a river flowing through it, and place a virtual box, a rectangle, as a probe at its center. You will find that the flow is unchanged inside your imagined box. What goes in to this box, to this probing box, will also come out. For example, the flow through the left-hand side may be equal to 2 kiloliters of water per meter squared and second. This means that the flow through the right side of this box will also be 2 kiloliters per meter squared and second. Approaching this mathematically, one can imagine making the box infinitesimally small. Making this probing box smaller and smaller does, however, not change the result. The flux, which is volume per cross-sectional area and time, the flux through this box is unchanged. Reducing the box to a point, one realizes that at this point the field lines are parallel, they do not diverge. Therefore, the divergence of the field at that point is 0. This illustrates that a lack of flux change is related to a 0 divergence of the field. The situation is quite different for the electric field shown on the top left. Probing the divergence at the point illustrated by the magnifying glass will give a result that is different from 0. In fact, the divergence probe will give a negative result, since the vector field lines converge at this point. If this was flowing water, the water would flow into a sinkhole and it would disappear. This shows once more that the divergence operation has the potential to identify sources and sinkholes in a vector field. In the electric case, a source is equivalent to a positive point charge at that point, and a sink is equivalent to a negative point charge. More generally, if applied in a particular location, the divergence operation indicates if a particular electric field originates from a distribution of source charges or not. If there are points in the field with divergence values different from 0, the operation of divergence shows that the field lines converge or diverge to or from these source charges that are located at these points. Since the existence of source charges at a point in space is represented by a non-zero charge density, a non-zero divergence is equal to a finite charge density at this point of probing. This is in fact just the statement of Maxwell's first postulate. It can be formally shown that convergent and divergent vector fields are also irrotational. These 2 situations are mutually exclusive. The opposite case, a rotational field, is therefore not convergent or divergent. This latter case is typical for magnetostatics. In magnetostatics, the field lines connect back up with themselves, and there are no sources and no sinks present in the magnetostatic field anywhere. Our probing box in a stream of water may encounter the situation shown here. In this case, on the left-hand side of the probing box, water is streaming into the box and water is streaming out of the box, so that the net flux through this left side is equal to 0 kiloliters per meter squared and second. On the right-hand side, however, the flux is outward at a rate of 4 kiloliters per meter squared per second. Integrated over the entire surface of the box, this means that there is a net outflow of water from this box. This means that somewhere inside this box there is a source of flow, and the field lines diverge. Making the box infinitesimally small, the point at which this source exists may be identified. One may imagine a beam of electric charges, for example, a beam of protons, whereby the beam has a finite radius. Such a situation occurs, for example, in the Large Hadron Collider at CERN in Geneva. There, the protons are accelerated to close to the speed of light and to very high energies. In the example here, the protons, positively charged, move in the z direction, and the situation is discussed in cylindrical coordinates. Since the protons move, in this example there is also a circular magnetostatic field that is symmetric with respect to the z-axis. We neglect this field in this discussion. This is sensible because in stationary situations the electric and magnetic fields are not coupled to each other. Although the protons are moving, the situation is quasi-stationary because protons moving to the right are replaced by protons coming in from the left. And from the outside, the situation looks like a static cylinder of protons. One can show, using for example Gauss's law of electrostatics, that the field on the inside is given by the constant charge density ρV divided by 2 epsilon naught times r, the radial coordinate, times the radial unit vector. On the inside, the field is therefore linearly proportional to the radial coordinate r. This is different on the outside. There, the proportionality is with 1 on r, and the equation is ρV divided by 2 epsilon naught as before, times capital R squared, whereby capital R is the radius of the cylinder, and divided by little r. In cylindrical coordinates, the divergence operator is given as shown here. Applying the operator to the field on the inside and on the outside of the cylinder, we immediately realize that the partial differentiation with respect to phi and z return a 0. This is because the field does not depend on phi or z. However, the partial differentiation with respect to the radial coordinate r is relevant for our discussion. Differentiating the field on the inside, we obtain a finite result of ρV divided by epsilon naught. In contrast, the same differentiation on the outside produces a 0. We therefore conclude that the divergence is non-zero on the inside and that there must be source charges present. In contrast, on the outside there are no source charges. Both observations are in line with expectation and in line with the drawing on the top left. It is interesting to note that on the outside of the cylinder the field lines appear to diverge. However, this is simply a consequence of the cylindrical geometry. The mathematical divergence is indeed equal to 0. This indicates that one has to be careful with interpreting the apparent pattern of field lines. Only the formal application of the mathematical operator will give a clear-cut result.